Welcome Math 107 students to the demo for lesson 23 on dividing polynomials and the factor theorem. In our preview exercises, we were looking at the long division algorithm that we learned in school for this particular division problem, 787 divided by 11. And in algebra, the division of two polynomials can be done using an algorithm or a process very similar to long division with our natural numbers. Let's start by looking at this long division problem again, but with a little bit of a twist. I'm going to take each of these numbers and I'm going to write them based on their place value. So 11 is 10 plus 1. 787 is 700 plus 80 plus 7. And now when I do my division, I'm really going to be focusing on the largest place value in my divisor, which is 10, and the largest place value in my dividend here, which is 700. And I'm going to ask myself, how many 10s go into 700? And my answer is 70. So one of the things that I notice now is that my answer is 70. So I'm going to write 70 above its like place value right here, 80. Notice where I put the 7 in my long division algorithm in our preview activity. See how we put it right above the 8? We called it an 8, but it was really 8 10s. It was really 80. Then we multiplied 7 times 11, and we got 77. Okay, but again, I pointed out to you some fallacies with that language that we learned. So what we're really doing is we're taking 70, and we're multiplying it by the 10 and the 1. So we're multiplying 70 times 10 plus 1. Remember, 10 plus 1 is just 11. So that will give us 700 plus 70. When we did it up here, we had 77. The next step was to subtract the entire 77. So now since I have 770, again, this was in the hundreds place and this was in the tens place, I have to subtract both of those. So one of the things I have to do is go in here and change both of the signs in front of the 700 and the 70. This goes to 0, and now I'm ready to start my process all over again. 80 take away 70 is 10, and I bring down my next place value, which is plus 7. And now I erase because I want to start this process all over again. I take my largest place value here, 10, and my largest place value in my dividend, and I say, how many 10s are in 10? And my answer would be 1. So I say now plus 1, and notice I'm right above my ones place. There's 1 10 and 10, so we get 10 plus 1. Now I've got to be careful to subtract both pieces here, so I've got to distribute that negative sign through. 0, and then 7 take away 1 is a remainder of 6. So my remainder is 6 over 10 plus 1, or 6 over 11. All right, so how do we turn this into an algebra problem? Well, let's see, everywhere we see a 10 here, we're going to replace it with x. So now our divisor becomes x plus 1, because we're going to replace 10 with x. And everywhere we see a 10, well, I don't see any more 10s, you might say, but remember, we can write 700 as 7 times 100, which is 7 times 10 times 10, or 7 times 10 squared. So if I replace the 10 here, or the 10 here with an x, that means inside here I have 7x squared. 7x squared. I'm just going to make this a little less thick, the x plus 1 on the outside. So we have x plus 1 out here. We have 7x squared on the inside. Now how would we rewrite 80? Well, 80 is 8 times 10. So if I replace the 10 with x, that would be an 8x. And 7 is 7. There's no 10s. 7 is 7 ones. So this is what we call the division of two polynomials. Notice I have a quadratic polynomial as my dividend and a linear polynomial as my divisor. And I start the same way. I ask, see, I find the biggest place value in each of these. Here I find my highest degree, right? X to the first power is my biggest degree here. So I say, how many x's can I divide into 7x squared? And if you need to, over on the side of your paper, you could just do your long division out this way. 7x squared divided by x is 7x. So notice I get an answer that is 1 degree less than the x squared. It's like my tens place. I have to put my 7x directly above my like term. I have my x terms right here. In the second spot, I put my 7x there. Then my 7x multiplies the x plus 1. So 7x multiplies my divisor, x plus 1. And when I do that, I get 7x squared plus 7x. And now remember, I'm subtracting both of these, so I've got to come in and change both signs. These 7x squared minus 7x squared gives me 0. 8x take away 7x gives me 1x. And now I bring down my plus 7. And now I say, how many times does x go into x? My answer is 1. And now I do 1 times the divisor, x plus 1. That gives me x plus 1. And I've got to subtract both of those, so I've got to change both of these signs. And I get 6. And my remainder is 6 over x plus 1. So you can, I hope you can see the relationship between doing this algorithm with numbers and doing it with long division of polynomials. So how would we check? How would we make sure that this is correct? It's always the same. We take our divisor, x plus 1, and we multiply it by our quotient, 7x plus 1, and we add our remainder. So let's see, we have x times 7x is 7x squared, x times 1 is x, 1 times 7x is 7x, and 1 times 1 is 1. And we add our remainder 6, and we get 7x squared plus 8x plus 7, and that's exactly what we started out with. Okay? So in the situation where we had our numbers and we wanted to check, our divisor was 11, our quotient was 71, and our remainder was 6. 11 times 71 was 781, plus 6 gave us 787. So when we have a division problem where we get a remainder, we say that the divisor 11 is not a factor of 787 since it doesn't divide into 78 evenly. It does not have a remainder equal to 0. All right, so let's bring this together with another algebraic problem, and we will go step by step again. So here we have a quadratic expression, and we're dividing it by a linear expression, just like we did a few minutes ago. So the first thing you always want to do is you want to arrange the terms of both your dividend and your divisor in ascending order. Descending order. So you want to have your largest place value, then your next place value, and your next place value. We say that's descending powers of x, right? So this first one is not in descending powers of x. So we want to put 6x squared first, 5x is where it is, and then our constant term is next. So I'm going to put that inside my division. That's my dividend. And my divisor should be written as 2x plus 3 if I do descending powers of x. Okay. So My step is always the same. I take 2x and I divide it into 6x squared, and when I do that, I get 3x. Remembering to place the 3x above the like term, the like place. So I place the 3x above the 5x, and now I multiply each term of the divisor. Sometimes students like to put the divisor in parentheses. So I multiply 3x times 2x, and I get 6x squared, and then 3x times 3, and I get 9x. And now I have to subtract the 6x squared and the 9x from 6x squared plus 5x. So I have to literally go in and subtract both of these terms. So I go in and I change both operations to their opposite. And I get a 0 here. And here I get a negative 4x. And I bring down my next term, which is negative 6. Let me erase this here. And now I start the process all over again. I say, how many times does 2x go into a negative 4x? That's right here. 2x goes into negative 4x. Negative 2 times. Put the negative 2 here. And then I multiply negative 2 times each term here, and I get negative 4x minus 6. And you like to see that because this is exactly the same, and when you change the signs to their opposite signs or inverse signs, you get a 0 and a remainder of 0. So this says that if you have 6x squared plus 5x minus 6, it factors to 2x plus 3 times 3x minus 2. These were always the factoring problems you didn't like doing because there were so many possibilities. We could have taught you how to do long division to factor, right? All right, so now we say that 2x plus 3 and 3x minus 2 are factors. These are both factors. They divide evenly into 6x squared plus 5x minus 6. In other words, the remainder is 0. Anytime your remainder is 0, you have found the factors. All right, suppose we have a polynomial function f, and it has zeros at negative 2, 1, and 3, all with multiplicities of 1. So we know at negative 2, 1, and 3, our graph will go straight through, cross over the x-axis. They all have multiplicities of 1. Since it has 3 zeros, we know that we can have a degree 3 polynomial here. We also see that we have 3 minus 1, 2 turning points. So when we get set to try to find the polynomial function for this, we know we set up 3 factors where each term that we're subtracting from x represents a 0. And we remember that our leading coefficient goes out front of the whole expression as a factor. So if I know that negative 2 is one of these values, it's a 0, negative 2, C1 here is negative 2, that's my first 0. X take away negative 2 becomes x plus 2. C2 is my next 0, C2 is 1, so x take away 1 is my next factor, and then finally C3 is the value x equals 3, x take away 3. So if f of negative 2 is a 0, then x plus 2 is a factor. If f of 1 is a 0, then x minus 1 must be a factor, right? Because if we put a 1 in here, we get a 0. If we put a negative 2 in for x, we get a 0. And finally, f of 3 is a 0. So x minus 3 is a factor of the polynomial. Now we can reverse that. We can say if x plus 2 is a factor, then we know f of negative 2 is a 0, because when I put a negative 2 in here, I get 0. If I know that x minus 1 is a factor, then f of 1 will give me an output of 0. And if x minus 3 is a factor, then f of 3 is a 0. So remember, this section was called dividing polynomials and the factor theorem. Here's some factors. So where is this all leading? Well, the moral of the story is, if you know a factor of a function, then you know a 0 of a function. If you know a factor, you know a 0. And if you know a 0 of a function, you know a factor. So that's important information. It shows you how to relate what you used to call your x-intercepts, that you now know are the values of x that make your function equal to 0, to their factors. Once you have the factors and the multiplicities, your only job is to find the value for the leading coefficient, and you have your whole equation for your polynomial. So let's summarize our findings here in the following theorem called the factor theorem. Let f of x be any polynomial. If f of c is equal to 0, then x take away c is a factor of the polynomial. C is a 0, x minus c is a factor, and vice versa. If x minus c is a factor of the function f of x, then f of c is 0. If you know one, you know the other. And you'll have a chance to work with some of this in your class lesson activities. Okay, speaking of lesson activities, here they are. If you have any questions, let me know. I'll be glad to help you out.